Okay, we're starting.
Move your eyes out.
Alright, settle down. I won't be able to project as much today, being a little under the weather. But I'm medicated, I have balls in my mouth, have a cup of tea here, just in case things get too scratchy. Yeah.
Oh, did you get your teeth out?
I didn't.
How did you
That happened many years ago. Huh?
How did you get holes in your mouth?
Halls, H-A-L.
Okay.
Yeah, I have a bit of a sore throat, that's helping me through. Yeah. I seriously thought about like canceling all my classes today, but it's like, yeah, exactly. Like when you're a student and class gets canceled, you're like, yay! When you're a teacher and class gets canceled, now it's like, damn, when am I gonna make up this class? Like, how am I gonna make up this class? I was kind of already behind already. Can't tell them coming on reading day, everyone's gonna be mad at me. It's like, you'd rather risk death than really put off a class that you don't have to. Because it's going to be like, well, if I die, I don't have to make up a class. So but if I survive, like this is something I'm going to have to deal with in the future. Like it's,
Try to get ahead.
But it's always a balance. You never know. Anyway, so today is a non-quiz week, which means I'm supposed to be like talking to you guys about being good math people. So let's actually, so last time I spoke about some general things, I just want to take another 10 minutes to give you another piece of the puzzle here. Just the general framework in which you want to operate. You're going to pick a goal, you're going to make it specific. You're going to have a reason why you need to reach that goal. That's going to help you when you're in very frustrating situations to power through. You are going to have a way to objectively assess yourself and have a plan to improve if it ever comes to that. And yeah, you kind of rinse and repeat those things until you meet the goal. And you do this on every test, every quiz, everything. Every time you go through this process. Pretty soon you'll be second nature and you'll go through it a lot quicker. If you're not used to going through this process, it will take you longer to study and get through things in the beginning. But in the future, it'll actually make things a lot quicker. You'll be a lot more efficient and it won't be so crazy. And I mentioned that specificity is actually very important when doing this. So to get better at quizzes, practice quizzes. To get better at tests, practice tests. To get better at homework, practice homework. It's very important that you're very specific when you're going through this process. So a lot of students, they study and they do all these other things other than the specific thing that they want to get better at. And yeah, it doesn't make any sense, but in math class, students do it all the time, right? You want to get better at basketball, everyone knows you should play basketball. You want to get better at doing a math test, people decide to do homework. They decide to study quizzes. They decide to read it. They decide to do everything except doing a math test. Doesn't make any sense in any other context, but people do this in math class. So make sure you're not doing anything that's blatantly that silly. To move on, let's actually talk about the actual skills you'll need here. And so this is talking about when you're studying, how to make sure you're being the most productive. You should be seeking to get certain things from your study, and this will help you to improve. You'll know what you're missing, the actual skills you need. Now, what I'm going to tell you, this will work for in pre-calc, calc 2, a bunch of other things, but you might need to add a little bit more. Calc 3 and higher. In terms of elementary math, the computational stuff. Require one more quality, which I'm not really going to talk about. But what is it that you're actually trying to cultivate? Now this is why, it's one of the reasons why I believe pretty much anyone can get good at math if they choose it. Because again, rules are kind of made up and we're just playing a game essentially. But the other thing that makes me pretty confident that if you actually put in the work, you'll actually get it done, is that the skills that you'll actually need are skills that most human beings have automatically. And that's one, form recognition. The ability to recognize forms. For example, you can tell when something is a dog, even if it's many different species. Like if I show you a Doberman, you will say that's a dog. If I show you a Shih Tzu, you go, that's also a dog. Right? If I show you a Husky, oh, that's a dog. The ability to do that form recognition. You recognize the form of something. Even though the specifics and the peculiarities might be different, overall you just know the idea of a dog, what that means. You can look at multiple examples and recognize them all as being in one category. They're all kind of the same thing. In the same way, you can look at this and you can say, that's a quadratic equation. And someone can say, well, look at this. And you should also be able to say, that's a quadratic equation, right? They have the same essential features. There's a number times something to a second power. And here you have a number times something to a second power. Here there's a number times something to a first power. Here there's a number times that same thing to a first power. Here there's something that doesn't involve that thing. Here there's something that doesn't involve that thing. These are both quadratics as far as I'm concerned. You can see something like radical 2 sine squared x plus 3 sine x minus 4. And again, you can think of that as quadratic. And a lot of the things that you do with a quadratic would work there. Just the ability to recognize a general form of something is very important. That is a skill you already have. Right? It's just now you're fine-tuning it to the mathematical situation. And the second skill you need, there are actually only two, is algorithm execution. And again, this is something that most people already have. Can you follow a sequence of steps that will take you from point A to point B all the time? Well, you're all dressed, so I know the answer is yes, right? You had to follow a sequence of steps to get dressed. You always put on your pants before your shoes, for example. That's just something you know. Pants go on before shoes. You don't actually literally think about it like a robot every time you're getting dressed. Oh, I have to put on this first and that. You don't think about it that way, but you do actually go through a process where certain things happen before other things. This is algorithm execution. And that is the second thing that you need to do, be able to do to be good at math. And as far as pre-calculus is concerned, that's it. If you know how to recognize a form and realize that there are certain algorithms that go with that form and know how to follow the steps to go through that algorithm, you are an A student. You don't need to do anything else. All you need to do now is to make it more specific. Okay? So once you recognize something as a quadratic, you will automatically have a bunch of algorithms in your head, or you should, that go with quadratics. You should know, oh, there's this thing called quadratic formula that connects with quadratics. There's completing the square that can work with quadratics. There's factoring, the AC method. There are a bunch of algorithms. These are processes in order to get something done that goes along with a quadratic. Once you can recognize what you're looking at and perform the right algorithm to get the result that you're looking for, you have solved the problem. That's it. That's all there is to it, really. But of course, again, that's very vague and general, so some tips in to actually cultivate these two skills. In math class, but this will work with anything technical. It'll also work with things non-technical too, but I don't really want to get into there. Because literally these steps that I'm telling you about, like when I was an undergrad, I used this with almost everything. Right? If I had a creative writing class and I got a bad grade in that and I wanted a better grade, I went through these sequence of steps. Being able to think mathematically, as we were discussing, kind of helps you with everything. If you are creative enough to apply it to other things. First, well, let's keep it step 0. Specificity. You always want that. I already spoke about that, so I'm not going to speak too much about it again now. That's the first thing. You want to be very specific, very detail-oriented, all that good stuff, which leads me to step 2. You are going to want to know definitions. By the way, this includes including but not limited to how notations work, vocabulary. A lot of people don't realize that vocabulary is actually super important to mathematics. Just nomenclature, how you talk about stuff, just language in general. That sort of thing. You want to be very good at that thing. Okay? So that's the first thing. 2, you want to make sure that you memorize rules, formulas, and I'll put for emphasis here exactly. Now you don't have to worry about this right now, but probably the nicest example I can give you is one from calculus. Don't worry about you not knowing what it means. I think you can see the idea pretty clearly. You go to calculus, you're going to talk about something called derivatives. You're going to learn about a specific rule called the power rule for derivatives. And that is a rule that says if you have d over dx times x to the n, this is n x to the n minus 1. It doesn't matter if you don't know what that means. If someone writes these symbols down here, it means you should do that thing. So for example, if I say d dx of x cubed, what am I going to do? Well, the thing that was on top, I'm going to move it down in front. And then the thing that was on top, I'm going to subtract 1 from it. So this gives me 3x squared, right? Now, like 4 weeks into your Calc 1 class, you're going to see that. But it doesn't matter. I can just tell you about that now. That's the rule, right? And there are times when I will ask the same Calc 1 students, okay, how would you do this one? And do you know what guesses I would often get? Well, wouldn't you do the same thing? Put the x down and subtract 1. And that is actually not correct. And the reason why, and that happens pretty often, the reason why is they didn't memorize the rules exactly. You see, the position of everything is actually super important. So when you memorize rules exactly, I mean, you should know what the particulars are. So for example, n here is a number, it's a constant. The base here is a variable, right? So this thing looks like d dx of a variable raised to a constant. Okay? Now if you look at this one, it's a different situation. It's not the same thing. It's a different form. It's like that's a dog. This is something else. But a lot of people decide because, oh, I remember that there was this rule where if something was up here and moved down here, and they just decide to follow this rule when they don't realize they don't have the form for the rule. See, this one is the constant is down here and the variable is up there. If I didn't give you a rule that says you can interchange these, you should not assume it's an actual thing. This is what I mean by memorize rules and formulas. Exactly. You should be aware of the positioning of certain things, what is the nature of the things in the respective positions, etc. You really need to memorize them. It's not like I kind of know them. The moment you start, well, it's kind of like this, you've done messed up. Anyone ask you about anything mathematical, and you're like, well, it's kind of like, you know, it's sort of when you do that, you're already done. What that means is, it's easy for a math teacher to give you a curveball in an exam and totally mess you up, right? If you need to say, this is what it is, this is the rule, this equals that, I can tell you what's in this position, what's in that position, what is the algorithm to deal with it, etc. So not only do you memorize rules, but you memorize them exactly. Because these are the rules of the game, right? Like, just like a chess piece. The knight moves in an L, specifically 3 squares one way and 1 square to either side. You can't change the length of the L, right? You can't do a B instead of an L because you feel like it. No, this is the rule that it's 3 squares one way, 1 square the other way, right? And all math rules are like that. If it were the case that the variable could be here and the constant could be here, there will be a separate rule that says that is allowed. There is no reason for you, if I write down a rule, there's no reason for you to expect something of a different form is going to follow that rule. It should not be assumed. If it's the case, I will give you a specific rule about it. Okay? So that's an idea. That messes students up all the time. and white chalk. And the next thing is to know strategies, right? And the above is what helps you I'll give you a recent example from this just last homework. Several students saw me about a particular problem. Now the numbers for everybody was different, so I'm not really gonna just say some random numbers. Something like a minus 1 to the 4th minus b plus 1 to the 4th over a minus 1 cubed minus b plus 1 cubed, something like that, right? And a lot of students were telling me, oh, this runs hard, I tried doing this and that and blah, 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 and I couldn't get to the answer. And when I tried to figure out what they were doing things like multiplying this out 4 times and expanding everything and doing all that sort of stuff. Now here's the thing. If you follow these rules, there are certain things you would know. So for example, when simplifying a fraction, you should be factoring. This is the opposite of expanding. So if you approach that by, I'm just going to multiply everything out, you're literally moving in the opposite direction of where you should be moving. Yeah, it's going to be a hard problem if you do that, right? You should be thinking factoring. We simplify the strategy for simplifying a fraction is factor the top, factor the bottom, cancel the common factors. That's the strategy, that's the algorithm. You should just know, if I see something, I recognize it as a fraction, that's the form, there's a whole line here. What's the strategy for simplifying that form? Well, factor the top, factor the bottom, cancel common factors. Once you just start indiscriminately expanding everything, you're going to be in trouble because you're not obeying the strategy, right? Now, when you know you have to factor something, how are you going to look at it? Again, there's another form here. You should recognize that this is the form of the difference of squares. That's the form of the difference of cubes. It's like a dog, right? Now it's like a different species of dog. Now when you think difference of squares, you think this idea here, right? When you think difference of squares, you think, okay, that means x squared minus y squared equals x minus y times x plus y. And that is correct. That's how the rule is stated in general. But if you realize, for example, just look at the top here. One thing you're going to notice is that if I look at a minus 1 squared, and then I square that, and look at b plus 1 squared, and then I square that, now, if I look at the a plus 1 squared, what does that remind you of? Right? I'm all over the place, my motor skills aren't that great. This guy here is like in the position of x in that rule. This guy here is like position y of that rule. It has the same form. Now specifically, it doesn't look really like the same form, but it's something squared minus something squared. Just like this is something squared minus something squared. It's the same form. So if I tell you, oh, you need to factor, and you look at that and wonder, well, how am I going to factor that? What you should be doing is think, do I have a rule that looks like this form? That's the first thing you should do. It's all about form and algorithm. Is there a rule that tells me about this form? Right? Now immediately there isn't, but there are other rules that tells you that these guys simplify that, like for example the laws of exponents. So because you have this roller decks of rules in your head, you can kind of see them imprinted on everything, right? Like you look at that and people say, oh, there's some to a 4th power, I have to expand, right? Someone who's good at math looks at that and sees difference of squares. And that's the difference. That's why one student will get A and another student won't. One student just knows to recognize the form. And once they have a form in mind, they know the algorithm. I can write this as that, right? And then they're going to do the same thing here. And then you rinse and repeat, right? So a lot of people got stuck on this problem and asked me about it because they didn't really know what they should be looking for at which time. One, you have to know the definitions, know the rules, know the strategies that go with the rules, and have the form recognition. Know when something random that you see really looks like a rule that you have, and it looks like it in the important ways, right? So for example, there's specifically a 2 here, which means you should not assume that this will work right away because the rule doesn't have a 4, it has a 2 specifically, right? So if you think this, well, it kind of looks like that, you have to know, is there another rule that can make me write this so that there's a 2 here specifically, right? Specificity, right? In the rule, there is a 2. It's not a 2 or a 4 or a 6 or an 8, it's a 2. Therefore, if I want to apply this rule, I need to make sure that there is a 2. And then I'm going to start looking, how could I get that to be a 2 if it's possible at all? If it's not possible to get it to be a 2, then you're looking at the wrong algorithm or thinking of the wrong formula. Right? So those are the 2 basic skills. That's just a little bit on how you want to start acquiring them. Basically start, so a lot of students when they're studying, they tend to focus on the examples, and you should focus on examples, but if you're sitting in a test or a quiz and you're wondering, what did Jhevon do in that one example that time again? You're already messed up. It means you're thinking about math the wrong way. When I do an example, you should try to be looking from this perspective. What rule did Jhevon apply to go through this example? What was he seeing? What was he thinking? Right? That's more important. You're not going to think, well, he carried a 2. Was it a 2 or was it a 3? You're never going to remember every specific example, every step of every example. What you remember is a strategy. It's like when you're putting on your clothes, you don't have to remember, last week did I put on the pants before the shoes? No, you're so familiar with the process that you kind of know automatically what follows. So once you understand the concept of putting on your pants before your shoes, it doesn't matter if it's jeans or leggings or it's shoes or slipper, you kind of have this thing internalized, right? That's what you want for your math. That's the goal. Every time you're studying, that's kind of where you want to be aiming for. So that's just a little food for thought. Think about it seriously. And if you want to, the more you can apply this in your everyday life, in everything you do, in everything you're thinking about, the easier and faster it will be for you to improve at math and anything technical. So just kind of practice doing that. So like, if there's a sign that says, these stairs say go up, and those stairs say go down, like I saw some of the kids today, running up the down, running up the downstairs. You're missing the point. The idea is knowing that there's a rule and doing what the rule says, right? This specific skill not only makes you a better citizen, it makes you better at math, right? You see a sign that says keep off the grass, if you tell yourself, you know what, I'm going to keep off the grass, right? No matter what. So it's seriously, like there are times when I say, remember, don't cancel across sums, and students fall into this mistake all the time. It's because they never seriously said, cancel across sum is a rule that I will not disobey. The sign says don't cancel across sums, I'm not going to cancel across sums. Now once you start fostering that idea in your mind, it becomes easy to apply it everywhere. You won't really do things just because it happens to be convenient at the time. You'll do it because it's the right thing to do, right? And you have to know what the right thing to do is. That's where knowing the rules and the strategies come in, right? So, yes, in the grand scheme of things, it probably doesn't matter which stairs you go up. But if you want to say, I want to improve my math skills, there are certain actions you should think of doing all the time. Recognizing forms, knowing the rules, following the rules. If you make that a habit, it falls easier onto the technical things that you're doing. Right? And there are a lot of things that people don't think about, like I said, that will really make things all better. Like that's wrong. I don't want it. That's wrong. For the record, you can't do that. Right? So, and that's another thing. There are a lot of times when I would go through an example and I would also make a note of what would be wrong to do in this situation. Like, so if I see something, a common error, I say, here's a common error, make sure you don't do this. Like those little blurbs, you need to pay attention to those too. They are just as important, if not more important, than the specific example I'm working on, right? So, know the specific examples just so you can actually see how to apply rules in different situations, but at the end of the day, when you're reading through an example or you're reading through your notes, that should be the eyes that you're reading with. I want to read so that I can see which rule is being applied every single step, how it's being applied, how I know it could be applied. There was a similar situation over here where we couldn't apply that rule. What was different about this situation than that situation? Like these are the things that you should be thinking about, right? If you're trying to memorize a particular example with the specific numbers, it's never going to work. It's a losing game. It's like, yeah, I know how to put on my clothes if it's jeans and Jordans, but what if I have shorts and Timberlands? Now I'm confused. No, it's the same thing, right? It's just that when it comes to math, people don't recognize that. You're always doing the two same things every time. At all times, you're doing two of the same things every time. People just don't recognize it because they get scared of math, and so they don't think with their common sense. They think with that brain that runs from the saber-toothed tiger. They don't think with the brain that, yeah, that's actually the same thing. This is the difference of squares. I can see it right here. So that's it. When you're studying, try to go with that kind of stuff, and I spent way more time than I should. But if you actually internalize what I just said, it's going to make things so much easier. It's unbelievable. And you're going to be that kid that your friends think is good at math, when all you're doing is just following these two simple rules in your head. And you're, okay, you want to say I'm good at math, it's fine. But yeah, it's actually, like I said, it's a lot simpler than people tend to think. And when people say math is simple, they often feel like, oh, you're being condescending. But no, really. There are two things you need to get a handle on. And if you just practice doing those two things very well, like with minute detail and focus, math is easy. At least up to like Cal 3. Then it starts. But once you're at Cal 3, you'll be mature enough to handle it. Yeah, but things start getting weird after Cal 3. But like, yeah, all the way up to Cal 3, these two things gets you A's on everything, if you can apply it properly. Let's move on to 1.3. Let's talk about algebraic expressions. Again, we're going slow with this one. Sometimes I like to go slow through the early sections because it teaches you the things that I was talking about, the simple, basic rules. At any given time, even a complicated problem is just a combination of little smaller problems. Once you know how to deal with the smaller problems, you automatically know how to deal with the complicated ones. So if you understand the basic rules very well and you understand their essence and you see them as templates and you can fit them on top of things, you'll be a lot better. So there are times when I'll define things that you kind of already know what they are, but that's the point. You kind of know what they are. And I want you to know what they are. And that can make all the difference. So let's start from the beginning. We're going to look at some definitions here. Constant. This is very general, because this will take you beyond Cal 3. Well, not really. For pre-calc, this is R. For pre-calc, Cal 1, Cal 2, it's always the real numbers. When I say a constant, I mean a real number. It's a synonym for a real number. There are other contexts in which that might not be true, but for us, it will be true. If I say constant, I mean a number, anything on the number line. Radical 2, 1.5, 17, doesn't matter. Something on the number line, that's what I call a constant. variable. This is a symbol. That can take on various constant values as indicated. Right? So I can say x is a real number, and just by me saying that means it's a symbol in which I can replace x with any number on the number line, and that will be allowed. If I say x is a positive number, it means this is a symbol with which I can replace any number on the number line that is bigger than 0, etc. So a variable doesn't have a static value. Its value will vary based on the situation or the context or anything like that. Constants, their value do not change. If something is a 2, it's always a 2 in all contexts. Term. A term is a product. You kind of think of it as one thing. So it's just a bunch of things that are multiplied together, usually a constant, well, pretty much always a constant multiplied by some symbols. Right? Once it's a product. So 2x is a term. 3x squared y is a term. 3 sine x cosine x squared is a term. It's a single entity connected by multiplication. It's a product. If I say 2x plus 3 sine x, this is 2 terms. You think of it as 2 separate things. You think of the addition as being a separating entity. Subtraction is also thought of as a separated entity. If something has a plus or a minus in between them, you think of that as 2 things. If you only have multiplication, you actually think of that as 1 term. And this actually reminds me of a question that came up last week, where several people were actually confused about something. It's about applying the distributive law. Note, distributive law. So remember, the distributive law was that rule that said this, right? Equals AB plus AC. And so that's the distributive law. That's a rule. It works. That's true. There are times, though, when you have a single term, and I would write something like that, and every now and then I'll get the question, well, is that equal to A, B, A, C? Right? Like, do I put the A on the B and the C? Or do I just write down 1A, right? And that's a mix-up in what a term is. You see, the distributive law tells you how to take one thing, distribute across 2 terms. Here, there's 1 term. So this is actually not the correct idea. You literally multiplied A 1 time, right? So if your A was a 2, and you have a 2 and a 2 here, notice that you're multiplying by 4, right? So that actually doesn't work. The fact that an addition appears somewhere actually changes the rules a little bit, and you need to be aware of this. I've seen students try to multiply out across products, and they attach the thing to everyone in the product. That is incorrect, because there's only multiplication here. It's really one thing. Distributive laws say you can go across several things, but a product is one thing. It's a term. Okay? And students who make this mistake is because they didn't understand that definition. Make sure you understand that definition. Right? A product is a term. It's considered one thing. Right? So you can't distribute a multiplication across those. You can distribute multiplication across addition. That is the rule. Know it exactly. There's no plus sign. Don't do anything that looks remotely like this. Okay? So that's just a a very common misconception. It's not super common, but it happens a lot more often than it should. What else do I want to talk about? There's something called a monomial. This is a term we're not going to use much. Binomial we'll use a lot more. Binomial. Also trinomial. So this is a term that is a constant times a variable to a whole number non-negative power. Right? That's a monomial, that's a monomial, this is not a monomial. Binomial, a sum of two monomials. Right? So like 2x plus 1 is a binomial, or 3x squared minus 5 is a binomial. Trinomial, sum of 3 term, sum of 3 monomials. And we have the more general guy here, which is called the polynomial. Poly means many, and so this is just a sum of several monomials. I don't know if several is the right word to use. Specifically, a polynomial in one variable, which are often the polynomials we'll deal with in pre-calc, calc 1, and calc 2. In calc 3, we start to deal with polynomials of several variables. Has the form an x to the n is an minus 1 x to the n minus 1 plus all the way down to a1x plus a0, where the ai are constants. And x is the variable in question. Okay. So this is just a number times x to some power, and these can potentially count down all the way to x to the 0 power. And we call that a polynomial. So like 2x to the 5 minus 7x cubed plus 2x minus 1 is an example of a polynomial. Here your n is 5, that would be the a sub 5. Your a4 and your a4 is 0, so that means there's no x to the 4 term. Your a3 is minus 7, your a1 is 2, your a0 is minus 1, etc. That's a polynomial. We kind of intuitively know what that is, but that's the general form of a polynomial. You can only have whole number powers here, positive. So if you have something like 2x to the minus 3 plus 2x plus 1, not a polynomial. Right? Because of the minus power. Or you can have, if you have a fraction power, not a polynomial. Polynomials have whole number powers that are 0 or bigger. Polynomials are very special functions, and once we go away from the whole number positive powers, we lose a lot of their special properties. For example, it doesn't make sense to plug in 0 into this one, but it makes sense to plug in 0 into that one, right? Polynomials, you can plug in any number you want on the number line. This does not have that property, and that's a pretty important property to not have versus have, right? Polynomials, you can plug in anything. We say the domain is all real numbers. Things that aren't polynomials, you kind of have to be careful of what you're plugging in. Polynomial can plug in without care. It's not the only kind of function like that, but it's one of the most important examples. Coefficient. The constant in a product. So if I say 5x to the 7th, this number 5 is called the coefficient. There's the idea of the leading coefficient. This is the coefficient of the variable to the highest power. So if I have something like 2 plus 3x squared minus 7x cubed minus 9x to the 5th, then minus 9 is the leading coefficient. It doesn't matter that it's not actually in the lead. That's not what it means. It means look for the guy with the highest power, the number beside him, that's the leading coefficient. Even if it's last in line, if you're reading from left to right, it doesn't matter. Like terms, this is going to be important for many things. When I say two terms are like terms, this means terms that are the same except perhaps. In their coefficient. So x, 2x, pi x, 3x, these are like terms. Right? They all have an x. The difference where they are different is the number multiplying the x, and that's okay. These are like terms. If I have something like x, if I have something like 2x, 2x squared, 2x to the 4th, these are called unlike terms. Notice they all have the same coefficient, but we don't care. The fact that the thing that's not the coefficient is different makes it different. Now knowing what a like term is important because the rule, when we start doing our arithmetic with all these symbols, knowing a like term from an unlike term is going to make a lot of difference. Let's start getting into some math. Adding and subtracting polynomials or terms. Process here, knowing the strategy, is to combine like terms. You add or subtract the coefficients. To make one term out of several. We call this process addition. subtraction is kind of like addition, except you're moving on the opposite direction on the number line. Addition you can think of as moving to the right on the number line by a fixed number of units. Subtraction you can think of as moving to the left. And again, starting out with some basic examples here. If I want to add these two polynomials, or I want to add these two polynomials. I have like 5 examples here, but I think that's okay. I think you'll get the idea. You probably get the idea with 2, but just to be safe, let's put in a third one. So that's with addition. I'll talk about subtraction after. So of course the idea here is you're going to look across the two things that you want to add and you want to find the like terms. So we notice here that the 2x and x are like terms, they look the same except for the coefficient. And the 4 and the 3 are like terms, they look the same except for the coefficient. So I add the blues and the pinks. We do this by collapsing them into one term where I simply add the coefficients. So technically I'll do the 2 plus 3 x's, and then I'll have the 4 plus 3. I add the coefficients and combine the several terms into one term. So this is going to give me what we all know the answer should be, 5x plus 7. This is a 1. 3x plus 7. Okay, so do the same thing here. There are the x squares. So you take 3x squared plus 4x squared, you get 7x squared. You take 1x plus 2x, and you get 3 x's. It's like the 3 apples and oranges idea. Take 2 plus the 1, you get 3. Here, similar idea. There's a minus 4x cubed plus a 2x cubed. So those combine to a minus 2x cubed. There's a 2x squared. There are no other squares. This is the only guy of this form, so he just stays by himself. He doesn't combine with anything. There's an x. He's the only one who's a like term, so he just stays by himself. He combines everything. And then there's a 9. He's just by himself also. So we have that as the answer. And I pretty much cross things out to make sure I'm not forgetting anyone. Sometimes you have something long and forget to add certain things. I'll just cross things out as I'm adding them. Subtraction is similar. You just need to remember the distributive law. So you might have subtract x minus 3 from 2x plus 2. So when you want to subtract one thing from another, the guy after the from, that guy goes in front. You put a minus sign, and you put parentheses around the other thing. That's where you need to remember the distributive law. You need to remember to put the parentheses around the other thing that follows the minus sign, because this negative sign has to be distributed. And so what this becomes is 2x plus 2 minus x plus 3, and then we now it looks like an addition kind of thing. We combine like terms, the 2x minus 1x, and the 2 plus the 3. So that just becomes 5. X plus 5. nothing crazy here. I don't think we'll get to anything too crazy today. On Wednesday we'll get to something that doesn't seem too crazy, but I'm pretty sure we'll find that most of us don't know it as well as we think we do. Yeah, that's kind of what I want to do. Another example, also remember PEMDAS. So whenever you're combining addition and multiplication and all these other stuff, you should remember PEMDAS. So if I want to say something like simplify, something too complicated, 5x plus 2x minus 2x plus 1. PEMDAS says deals with what's in parentheses first, and you normally deal from the inside out. So I first worry about what this guy's going to be, which the distributive law tells me that that's going to happen. And now here, this is essentially a parentheses here. We can combine like terms in these parentheses, that's minus x minus 1. And then we can apply the distributive law there. And then we'll combine these like terms. So that simplifies the 3 2s. Nothing too crazy so far. So that's addition, add like terms. What's a like term? Any two things where the only place they're different is their coefficients, if that. Multiplying. Process. Someone says, how do you multiply so two things? Well, apply distributive law. Is going to be the first step. 2 is going to be combined like terms, like we've seen before. From now on, that's how you multiply things. There's a 2-step algorithm for multiplication. Apply distributive law, combine like terms. No matter how it looks, no matter how complicated it looks, multiplication itself is never more complicated than that. You are always doing these two things, no matter what two things you're multiplying. So to multiply 2 by x plus 2 over multiply x plus 2 times x minus 3. So essentially you're applying the distributive law. Now by applying the distributive law, you can even get more specific as to what that means. That means take each term in one, multiply everything in the other. That's what I mean by apply distributive law. So here I'm multiplying two things, the 2 and this thing. I'm going to take every term in one of these things and multiply everything in the other one. So here's the 2, that's everything in this term. I'm going to multiply everything in the other one. So that's going to give me 2x plus 4. Okay? 2 times the x, 2 times 2 is 4. And similarly here, I'm going to just take the first one, take each term here and multiply everyone over there. So I'm going to take the x, multiply everyone over there. Then I'm going to take the 2, multiply everyone over there. And so this is going to be x squared for this arrow, minus 3x for that arrow. I've taken the x and multiplied everyone. Now I'm going to take the plus 2, multiply everyone. Plus 2x, which is this arrow, then minus 6, which is this arrow. Now, some people like to call this FOIL. You'll notice here that what I did was I multiplied the first terms together, then I multiplied the outer terms together, Then I multiply the inner terms together. See the ones that are on the inside? And then I multiply the last terms. Now this, we take the first letter. This is called FOIL. Now a lot of people use that word incorrectly. For example, there are times when I would see someone go, like even this. I'd say, how do you simplify that? They say FOIL it. Well, it doesn't make sense to say FOIL in this situation because it doesn't match the mnemonic. But all in all, you can forget FOIL and your mathematical life will not change at all because FOIL is just a specific application of this. And this applies all the time, even in the case where FOIL works. So you can literally forget FOIL and just know, take everybody in one thing, multiply everybody in the other thing, combine like terms. So at this point we're combining like terms. There's an x squared, there's no other x squared. We're going to take this plus that gives me a minus x. Goes to our like terms, and then there's a 6. So that's that. And this is we multiply out. So again, this works in general. So if I were to say something like x plus 2 times x squared minus 3x plus 1, right? FOIL is not going to help you here. If you multiply the first terms, the inner terms, the outer terms, and the last terms, you're going to miss a lot of terms, right? So FOIL isn't the way you want to think about it. You think about it the way I told you. Take everyone here, multiply everyone there. Then you take this next guy, multiply everyone. And you just keep doing this process until everyone is multiplied out. Then you combine like terms. So I'm going to take x, multiply everybody. That's going to give me an x cubed minus a 3x squared plus an x. By the laws of exponents, we already discussed that. Then I'm going to take the 2, multiply everybody. That's going to be 2x squared minus 6x plus 2. Once I've done that, I'm going to combine like terms. There's an x cubed here, no other like terms. There's an x squared and an x squared. These two are like terms. I can combine those. There's an x and an x. These two are like terms. I can combine those. And now there's just a 2 left over. So that is the answer here. That's how we multiply it out. That's multiplication. That's what it means. So take everybody in one thing, multiply everybody in the other thing, combine like terms. We say you multiply. Now, there are some special products. These are the ones that we kind of know beforehand how they're going to multiply out. So we can kind of not have to worry about this idea and just kind of do the other idea. These are the familiar things like difference of squares. You see something like this, it will always multiply out to something like that. It's called difference of squares. And we also have the difference of cubes. If you see something like this, it will always multiply out to something like that. Now you can do what I did here, and it will take you a while to collect things and then figure out what it is. But that pattern is always going to be a thing. It's called the difference of cubes. There's also the sum of cubes. That's a special pattern that shows up pretty often in classes like this. So if you're multiplying out things that look like this, they will always multiply out to the cube of the first thing plus the cube of the second thing. There are things called perfect squares. And we'll take advantage of this pattern when we talk about things like completing the square, etc. This is just when you're multiplying one thing by itself. Okay, that when you take a plus b times a plus b, we know that that gives us a squared plus 2ab plus b squared. And if you have a minus b squared, a squared minus 2ab plus b squared. Now, everything I just wrote down, by doing multiplication as I described to you before, you will get these answers. However, These guys show up so often, it's worth memorizing them, so you don't have to go through the calculations. You'll just know that side leads to this side, and vice versa. So these are called the special products. At least the ones you need to know for this class. I think we're, a new example of that. We've seen it so often so far. Let's move on to the next important thing, factoring. It's a very important process, and I can tell you from experience, most people don't know it as well as they think they do. A lot of people mess things up because of factoring. Either they don't know that they should be doing it when they should, like the example I pointed out earlier. Like some people just don't know that simplifying a fraction means factoring, right? Or sometimes they do it incorrectly, like they don't do the distributive law very well or something like that. It's a very important thing to be able to do. Helps you with a lot of things, helps you simplify a lot of things, also helps you solve equations, and simplifying solve equations a lot in mathematics. So understanding factoring is a very important thing to understand. So we are going to go over some basic processes that you can do with factoring. Probably won't get through all of them at this point, but then I'll give you a general process where you just kind of know. If I give you any random thing to factor, you know I'm going to do this first, this second, that third, that fourth. There is an algorithm for it, right? It's not something you have to kind of figure out. It's something you should just know how to do. This is the first thing that happens. This is so we'll build up to that by the next class. But let's just say what this is. It's the opposite of multiplying out. Which we call sometimes expanding. I mentioned this before, so I'm not even gonna. Okay? So if I take a minus b and a plus b, and I multiply out according to the rules of multiplication, and I get a squared minus b squared, this is called expanding. There are very specific instances where you want to expand. There are other specific instances where you want to factor. Factor is simply the opposite process. Factoring is going from here, where we have a sum of separate terms, and we want to transform it into one term, of just a bunch of things multiplying each other. This is called factoring. There are times when we want things spread out, and there are times when we want things compressed. Expanding spreads them out, factoring compresses them. And different situations might make this convenient at different times. You should know these situations. Some pretty common ones, simplifying fractions and solving equations. You're always kind of thinking factoring in these situations. Expanding will usually get you in trouble. At least sometimes you might have to temporarily expand something, but the goal of temporary expanding is like cancel common terms so you can refactor at the end of the day. Right? They're going to be, factoring is going to be very important. So the first process you're going to want to know with factoring is called GCF factoring. Right at 12:45, right? Mm-hmm. Okay. So GCF, this stands for greatest common factor. Again, I'll give you a summary at the end, but pretty much when you're factoring any random thing, this is the first thing you're going to look for. It is always step one in factoring. Figure out who the GCF is, if there is any, and factor it out. So this is greatest common factor. What it is, I defined LCM before, so I'll just piggyback on that example. Pretty much almost same as LCM. Which we called LCD at times. I told you specifically how to find that. Factoring, by the way, was involved. You factor a bunch of stuff, you pick all the products with the highest powers. This gives you the LCM. Greatest common factor, very similar process. You're going to factor everything, but this time you're going to take the lowest powers. Except you take the lowest powers, not the highest powers. So this is the largest term that divides into all other terms. Even. So there's no remainder. So that's called the GCF. How you compute it? Pretty much same as LCM. You start out the same way, except you pick out the lowest powers now. So how does GCF factoring happens? So, for example, you look at x squared plus x. I know I'm starting simple, but we can learn a lot from these simple examples. What you'll notice is, of course, the root word, one of the root words here is common. So you want to find something that is common to everybody, something that is in every term. You'll notice that x is common to every term. Now, GCF factoring means you pull out the GCF and you put parentheses to hold what's left over. So I'm going to pull out, here are the common terms. There's an x to the second power, there's an x to the 1 power. GCF says take out the lowest powers. It is always the lowest power, every single time. Doesn't matter what the powers look like, always the lowest power. Okay, so we're going to take out x, we're going to left with x plus 1. So notice that if I were to multiply out, I would get that back by the laws of exponents. But one thing I also want you to notice what actually happened for me to do this, and this is going to help you with the more complicated problems when you think of it this way, is once you pull out something to the lowest power, which is 1 in this case, what actually happens to the things that are left behind? Most people don't really know or even think about it, but here's what happens. The thing you pull out, when you go to the like term where that thing is, the result of pulling this thing out is subtracting the power. So over here, what's going to happen is I'm going to have x to the 1, and then I'm going to subtract 1. Why am I subtracting 1? That is the power I pulled out. How do I know that? Because the laws of exponents tell me when I multiply it, I'm going to add it back to get the original. Most people don't really realize this, and that messes them up. And so now what happens is you have x to the 1 plus x to the 0, but what is x to the 0? Well, that's 1. Again, by our laws of exponents. So this just becomes that. Now, most people jump from this step to that step without really thinking about what happened in the middle. But understanding what happens in the middle really helps you with more complicated problems. So, for example, this one. Now, I put this on the quiz. A lot of people got it wrong. It's probably been on 2 quizzes by now. It was on quiz number 1. And I can tell you, sometimes my calculus kids mess up here. So here's an example of that. You've seen problems like I put problems like these before in your quiz, I'm pretty sure. You've seen things like that before. Okay, what do? Factor. Now remember, first thing you look for is GCF. What is in everyone at the same time? So you are going to notice a few things. For example, you're going to notice that there's a 2 in everything. Why? This 4 is a 2 times a 2. So there's a 2 to the 1 times a 2 to the 1, which is a 2 squared. This 6 is going to get a 2 times a 3. So there's literally a 2 in every coefficient. What else we're going to notice is that there is an x in everything. There's an x here, there's an x here, there's an x here. So x is a common term and 2 is a common term. So in order to factor this, the first thing I'm always going to do is pull out the GCF. So I'm going to pull out 2x. Now the question is, what power do I pull out? It is not 1/2. What is the rule? You always pull out the smallest power. Now, the powers of x are 3/2, 1/2, and minus 1/2. Who is the smallest? That is what you pull out. What is left over in the first term? What is left over here? Is it x? Right, now the simple idea isn't so simple, right? It's because you're underestimating the importance of what just happened, right? And a lot of people get mixed up. It's really a simple rule. What happens? You subtract the power. So what's going to happen here? The power of x that's left over is going to be 3/2 minus a minus 1/2. X squared is what's left over because of that rule, right? So here we're going to have 2x to the minus 1/2, right? Suddenly I throw fractions and everyone's brain freezes. It's the same thing. It's exactly the same rule. This is what I'm trying to talk about. Form recognition, algorithm execution. I know what it means to factor out a GCF. Pull out the thing that's common, subtract the powers. It doesn't matter that the powers are fractions. I pull out the thing that's common, subtract the powers. This guy is going to move out, well, here's a 2 squared. I pull out a 2 to the 1. So that what am I left over with is a 2 to the 2 minus 1, which is just a single 2. Then I'm going to be left over with some power of x. What power of x? Well, it's going to be a half minus a negative a half. Right? Well, let me put it up here so it simplifies later. So that is just x to the 1 that's left here. Minus, well, I pulled out a 2, so there's a 3 left over. And since there was an x to the minus a half, what is left there now? I keep forgetting. That's to the minus a half minus a half, which is a minus half plus a half. So it gives you 0, which means there's no x's. So that would be the first step in that factoring. Now this we'll talk about next time. This is called a trinomial. How do you factor that? Right. But most people get lost on this first step. And it's because they don't really know what they're doing when they're factoring. Right? Start understanding the simple things and you realize the complicated things, it's just applications of simpler things. We'll stop there. We'll pick up with this next week. Well, on Wednesday. I'm very out of it. Thursday. Oh my God. Okay, I'll see you guys.